We'd like to invite our next speaker, Tamara Grossman. If we can.
All right.
Tamara.
Welcome all back after the lunch break. It is my pleasure to introduce our next plenary speaker for the optimization block that happened yesterday. So Professor Peter Richtarik is a professor at KAUST. Before he was a professor at the University of Edinburgh. Among other things, he's also a Turing Fellow at the Alan Turing Institute in London. Peter's work is centered around optimization of machine learning. He also works on theory of deep learning, and he's one of the pioneers and co-inventors of the idea of federated learning. And yeah, I believe that today he will speak on how one could use second order method with randomness for optimization of neural networks and so on. So please, Peter, yeah, the stage is yours.
Oh, thanks a lot for having me at this beautiful virtual workshop. It's a great pleasure. I haven't been back to the UK for quite some time, so it's nice to be back there this way. So I'll talk about second order methods and randomness. The idea behind this is the following. As soon as randomness entered optimization, which depends on how you count, this was maybe 10 years ago. If you count maybe properly, then you can go as far as maybe 70 years back. But the renewed interest in randomness in at least continuous optimization is not dating back too far. People were working on first order methods, trying to understand how this works. And the community has been very busy with this for a decade or so. And the attempts of combining randomness with second order methods, they're very sparse. So people don't understand how this works very well. The literature, as I said, there's some things that we know, but much of it we don't know. And this is an attempt at maybe convincing you that this is not very easy, and at the same time offering one solution, which seems to be very easy and which escaped researchers over this last maybe decade or so. So this is joint work with, let me see how this works. This doesn't work. So, okay, maybe this is what I should be doing. So this is a joint work with my students, Dmitry Kovalev and Konstantin Mishenko. So this work wouldn't be possible without them. Dmitry started as a MS PhD student in a combined program, but now as of January, he's a PhD student. And Konstantin started as a PhD student. He'll be finishing this year. We have presented this work at a NeurIPS workshop, so we have a poster ready. So those of you who don't want to listen to me, you can just go to this link and read this very quickly in 5 minutes and you're done with this. I will not comment on this much further. So let me introduce the problem. The problem is essentially the problem that almost everybody looks at when you look at a random paper in ICML or NeurIPS, and they talk about machine learning and optimization. Most of it is finite sum optimization, where you want to be minimizing a function which is average of many other functions, and that's the case here as well. So the dimensionality of the vector that you want to find could be thought of as the number of parameters in your model, and n could be thought of as the number of training data points. But n doesn't have to be that, could be the number of machines, and then fi, each fi would be average over the data points stored on that machine. But let's think of n as being number of data points. These functions here will assume, and now I don't actually see what is written here because of all of these. Okay, now I think I'll see this. Good, I managed to move this around. So I'm going to assume that functions fi are really beautiful and simple. The structure is very simple. They're strongly convex and smooth. And they'll be second order smooth, so the Hessian will be Lipschitz. I'll define this a little bit later. So essentially, I'm assuming everything nice about these functions, notice that I'm very far from assuming something like non-convexity and going even beyond convexity into much more narrow class of functions, so strongly convex functions. So this is the problem I want to be thinking about. And here are some examples to keep in mind of what these functions could look like. So for instance, if you are interested in the classical problem of L2 regularized least squares, then this Fi will be, well, L2 regularized squared loss, or this could be logistic regression. Again, you have this logistic loss plus this L2 regularization. And think of this AI vector in both of these cases as being the data vector. Y would be a label. So this is binary classification here, let's say, or regression. And lambda is the regularization constant. But there's many other possibilities. I will not look at any of these particular examples, but the generic one where Fi is just anything that is strongly convex and smooth enough. So now the outline of the talk is that I'll first try to convince you very briefly that first order methods are great, but not so great. So that's the first point, and I'll mention why they're not so great and what is the issue with all first order methods. And then this will motivate why we should be looking and why we're looking in this talk beyond first order methods to second order methods. But we still want to keep stochasticity because that's important. And then I will introduce a stochastic Newton method and a stochastic cubic Newton method. This is this color indicates that I'm actually moving to the actual content, the novel content of this paper. All of those, the point 1 and 2, these are just introductory, and then I'll conclude with a few experiments. Good. So feel free to interrupt me at any time. I'm not worried about this at all. Like, actually, I prefer if you interrupt me during the talk rather than keep your questions till the end. So anytime something is unclear, just say so. So from very far away, if you look at first order methods, then you can think of them as being methods which revolutionized this when randomization is thrown in, optimization in the last several years. There's lots of literature on this, and roughly speaking, this literature can be partitioned into two big groups, and one is where the n is big, and the other one is when the d is big. So either the number of data points is huge, and that is the problem, or the number of parameters is huge, and that is the problem. When you think about problems where n is huge, then you think of methods such as stochastic gradient descent, dates back to Robbins-Monroe 70 years ago. And when you think of big T, then randomized coordinate methods or randomized subspace descent methods more generally, popularized by Nesterov from 10 years ago, they become the state of the art. And they are state of the art both in theory and in practice. So you wouldn't use the non-randomized versions anymore because the randomized versions are really much better. But the downside of all of them, all of these first order methods, is that they all suffer from conditioning issues. So what do I mean by this? So this is what I mean, but I'm clicking on the wrong direction. So, okay, this just keeps going in circles. Okay, so here I am. So we'll be focusing here on the big data problem, not the big dimensional problems. So n is really huge, and d will be of reasonable size. In fact, you can think of these being 10,000, something small. And the results are interesting even in the case when d is 1. So we'll completely throw away any consideration of d being big, and we'll only focus on n being very big. So here is a very high level explanation for why stochastic methods are better than deterministic variants. So this is what happens when you look at the theory and when you look at the implementations. The number of iterations increases when you use stochastic methods compared to their deterministic counterparts. So this is bad. But then cost per iteration decreases, which is good. And then the question is, do you save more than the extra costs? And the answer is yes. So if these methods are designed properly, then you save more. And this is why these methods are better in theory and in practice. So this is what always happens when you look at any kind of a method of this type. And here is just one example, one slide, where I show you how gradient descent works compared to stochastic gradient descent. So we have a very simple L2 regularized least squares problem with just 2 dimensions. So So I can draw this and 14 data points. So 14 is big on this slide. And gradient descent in one iteration looks at all of these 14 data points. Okay, so it takes pass through the whole data set and takes a gradient step, which is nicely orthogonal to these contoured lines, to these level sets. And again, gradient descent looks at all the 14 data points again before taking the next step, and so on and so forth. So by the time I take, let's say, 5 passes over data, I'm already, let's say, closer to the solution than before. Maybe this is a little bit exaggerated. In 5 steps, I wouldn't be this close to the solution. So this is not an actual run. This is just some depiction of what's going on. Stochastic gradient descent, on the other hand, in each iteration, you only look at one random data point. So out of these 14 data points here, I'm looking at the second. And nobody says that if I compute a gradient of the second loss function, that this is actually going to improve my overall loss function. So I'm going to move somewhere. Then I look at the 13 data point and so on. So I keep doing this. And I zigzag my way around all of this. But notice that by the time I go through all the 14 data points, I'm already closer than one step of gradient descent to the solution. And this is really why these methods are better. So each iteration much cheaper, but a number of iterations goes up. Good. So now the key thing to keep in mind is that all these first order methods, not just SGD, and I'll mention some of them on the next slide, they suffer from conditioning issues, which I'll explain what this means. And much of the research is actually focusing on trying to figure out some ways by modifying the algorithm to somehow get rid of this issue or somehow make it smaller. So for instance, preconditioning by the name itself is some kind of a technique which is going to try to decrease the dependence of the algorithm on the conditioning of the problem. Momentum acceleration, again, but this is just a very particular way to accelerate the method theoretically so that the dependence on the condition number, let's say, is not kappa, but square root of kappa, not linear, but square root of that. Variance reduction, yet again, the same story. Adaptive step sizes, such as Adagrad, Adam, all of the same story, smaller dependence on the, better dependence on the conditioning, mini batching, point sampling, and so on and so forth. So here's a few of these algorithms with their iteration complexities. And here, just for simplicity, I'm going to assume that a total function is mu f strongly convex, which is here. So you have this quadratic lower bound for f at every single point. And it's LF smooth, which means I can sandwich the function between these two quadratics. And every single fi is going to be convex. So I have a linear lower bound and LFI smooth. So I'm going to assume this for simplicity. And then the two most celebrated methods are gradient descent and accelerated gradient descent of Nesterov. And as you can see, gradient descent depends linearly on the condition number, which is LF divided by mu f. So this is the definition of the condition number. And the accelerated gradient descent depends as a square root of the condition number. So this is much, much, much better if the condition number is very big. But the number of gradient evaluations one has to do in each iteration is n, because one has to take the full data pass looking at every single function, every single data point in order to compute a gradient. And this could be n or on, 3n, 2n, or something like this. I'm just writing down n. But you can see that acceleration already helped the conditioning of the problem. Now, when we throw stochasticity in here, you could have stochastic gradient descent, let's say with uniform sampling, when I sample every single data point uniformly with probably 1 over n, then what happens is that I still maintain logarithmic dependence on 1 over epsilon, but now the conditioning goes up because now the condition number is max of LFIs divided by mu f. So the mu f is the same as here in gradient descent, but max LFI is going to be bigger than LF. This is because of these inequalities here. So LF is the smallest of all of them, then average of LFI is a little bit bigger, and max of LFI is even bigger, and so on. So the number of iterations goes up because the conditioning goes up, but this goes down. So that's exactly what I was saying. This goes down by a factor of n compared to n, but this goes up, but not by a factor of n because of this inequality. And this is why the method is better. But here I'm assuming implicitly, in fact, that I'm working with so-called overparameterized models where the gradient at the optimum of every single function, so every single data point is 0. Under this assumption, this is what happens. Once you don't assume this and you run this method SGD just naively, then you don't get logarithmic dependence of 1 over epsilon, but a different dependence. And there's a technique how to still resolve this, and this technique is called variance reduction. So variance reduced methods, they don't need to assume overparameterization. They don't need to assume this. They're still able to recover logarithmic dependence on 1 over epsilon, which means linear convergence. But then you get this extra plus n here, which makes sense. I will not go into explaining why. And there's many methods in this category: loopless SVRG, Saga, SVRG, and so on and so forth. There's many of them. And then you could just continue this, and this is why there's massive literature on this. You can combine this now with acceleration, improve this further, and so on and so forth. So there's additional tricks. But what I want to manage to do with this slide is that all of these first order methods depend on this pink quantity here, on the conditioning, and there's just no way around this. There's always going to be some dependence on the conditioning, and the dependence could be improved. So acceleration improves compared to this, and so on and so forth, but there's always dependence on the conditioning. And the question is, can we do something about this? And this is what I'm going to be talking about in the rest of the talk. So maybe I'll pause here for a few moments in case there's any questions about this part. So I don't know whether you are unmuted or whether I should be reading the chat here, because I cannot hear anything.
Yeah, we don't seem to have any questions so far. So perhaps if you can continue, and if there is a question, then we might interrupt you if that is okay.
Okay, so just shout. So even when I'm saying something, just say I have a question. Don't wait for me to stop. Okay, good. So beyond first order methods, recently there's been interest in pushing this direction as well. And beyond first order methods doesn't necessarily mean second order methods, could mean zero order methods, something like this, but I'm focusing on second order methods. And you can look at it at NeurIPS last year and ICML this year. There are workshops dedicated to this field. So there's interest in the machine learning community in investigating what can we do with second order methods. We need to keep randomness around, otherwise we're underperforming and these things don't scale, but how to combine randomness and the second order method. So what do I mean by second order method? Well, the most fundamental second order method, let's say, is Newton's method. From the optimization point of view, this is what it's doing. You take the current xk and you subtract the gradient, but instead of the step size, you get inverse of the Hessian. Okay, so in some sense, all of the step size rules in gradient time methods, they are somehow estimates of the largest eigenvalue of this matrix in some sense, if you can think of it that way. So this is Newton's method. And why is Newton's method interesting? So one of the things that makes this a second order method is that from convergence point of view, that it has a local quadratic convergence. And moreover, it's independent of the condition number. So once you're close enough to the solution under sufficiently nice conditions, such as strong convexity, Lipschitz of the Hessian, there is a quadratic convergence, and the convergence doesn't depend on any conditioning. So this is really beautiful, and we don't see anything like this for any of these first order methods. And the question is, can we do something like this, but with randomization? Unfortunately, we can't. So up to now, even though there's lots of papers on this topic, it is very difficult to make second order methods randomized in a meaningful way. So there's lots of papers which lead to improvements in practice, but in theory, the answer is really no. So let's, well, okay, maybe I'll just skip this. And in case somebody's interested, I'll talk about the big D regime, because in the big D regime, where the dimensionality is huge and N is not very big, in fact, randomization and second order methods were married already in the last several years. So there's some success stories there, and I plan to just have these two slides on this, but I'll just skip through this since this is really just tangential. And in fact, I will just focus on the big N regime right away. And I'll start with 2 attempts at handling the big N regime. And these, I will say, in some sense, are good ideas, but ultimately fail if our goal of what we expect of randomization and second order method, the randomized second order method, is high enough. And I suggest that we should have very high expectations. So the first thing you may think of is this. Since we're solving the problem of minimizing finite sum, maybe, and since SGD is interesting method, maybe you may think of doing something like this. So this feels like doing second order SGD. So you select one I index uniformly at random, and you take a Newton step on that function fi only. Okay, so if this I was not here, if I was doing the Hessian of the full function and the gradient of the full function, this is just the Newton's method. And I know everything is perfectly fine then. I get local quadratic convergence. But I want to randomize, so I do this for a random index I. If this inverse of the Hessian is not there, then this is simply just SGD. Okay, so I'm modifying SGD by this sort of preconditioning by the local inverse Hessian or stochastic inverse Hessian. Okay, so this looks like a good idea. Unfortunately, this doesn't work. And by this, I mean that this cannot possibly have better rate than SGD, than the first order method. And the reason is that there is actually a class of problems which satisfy all the nice properties about FI. So you can have strong convexity, smoothness, everything that you want about FIs. In fact, there are quadratic problems of this type where this method actually is equivalent to SGD. I will not go into the details, but you can look at this paper that I've written with Martin Takac, Stochastic Reformulations of Linear Systems. And there you'll find a description of this type of methods. And the brief explanation here is that for those types of problems, this inverse Hessian applied to the gradient just happens to be exactly equal to the gradient. And that is because this stochastic gradient just happens to be eigenvector associated with this matrix with eigenvalue 1. So the problem is cooked up in such a way. So this, for this reason, this cannot work. So maybe I'll pause here in case there's any question about this.
So I would perhaps have a question about this. So this class of problems that satisfies the nice properties of strong convexity and smoothness, and that for which attempt 1 fails, is it a large class of problems, or are they specifically constructed cases?
You mean for the property that I just mentioned, that the stochastic gradient is the eigenvector of this inverse Hessian? Or you mean just the big class that I'm studying? Well, for the big class that I'm studying, so functions with the Lipschitz Hessian and functions which are strongly convex, obviously it's not a very big class of functions. But this is exactly the class of functions for which Newton's method is known to converge locally quadratically. So we should at least be able to do that. So going beyond this is more difficult. One can assume some other things. But this is a classical set of assumptions. And this counterexample, these are problems related to linear feasibility. So when you want to just solve a system of linear equations and you want to use methods such as Kaczmarz method and so on, you apply stochastic projection type algorithms. And in fact, a stochastic projection type method for a linear feasibility problem would look like this. This is explained in this paper, that even randomized Kaczmarz method can be written in this way. But randomized Kaczmarz method is known to be, this is a randomized first order method. But at the same time, it can be viewed as a randomized second order method of this type. And this is somehow why one can't really get this second order property out of the behavior of such a method. So this looks like a naive idea for what an algorithm which combines second order information and randomization could look like, because it looks just like SGD, but you throw in second order information, but it's not enough. So this is not the right idea.
What if one considered more indices? So if one did not consider just a single tiny example, but
yeah, so that's not going to help. So that idea is called mini batching. it helps in the sense that you get a mini batch version of a first order method. So so the rate improves a little bit, but at the cost of evaluating more stochastic Hessians and stochastic gradients. But there will be no second order behavior of that algorithm. When you prove convergence, there's some lower bounds, and there will always be dependence on the condition number, even with mini batching. So unfortunately, that is not going to help either.
Thank you.
Yeah, so this is a failed attempt, and here's another attempt. Let's do something maybe, and in fact, your idea is used here, but well, actually maybe in the same way as you just said it. And the idea is, well, let's, instead of using just one stochastic gradient and one stochastic Hessian, let's just do mini batch. And this mini batch here for the stochastic Hessian would be the set SHK. So in each iteration K, you may choose a different one. And the same thing for the stochastic gradient. So SGK is the set of data points for which you compute the stochastic gradient and you average them. And then you may say, okay, if these mini batch sizes, if the cardinalities of these two sets, of these denominators here are large enough, then this HK matrix is going to be a good enough approximation of the Hessian, and GK will be good enough approximation of the gradient. So maybe this should behave close to how Newton's method behaves. So this intuition is correct, but unfortunately, you need to have really, really huge mini batch sizes. So in some sense, this is a sensitivity analysis of Newton's method. So the question is how much can you throw out from the full Hessian, so from the average of all the Hessians and from the full gradient, which is the average of all the gradients, so that you still retain some second order properties. And it turns out actually not much. You really have to be almost there with the full size. And in fact, sometimes the theory is so disappointing that it will suggest mini batch sizes which are larger than the actual data size that you have. And that, of course, cannot work. So roughly speaking, what you get is O kappa over epsilon squared, where epsilon is the accuracy that you want to achieve. And this could actually be even larger than n. Right? So this is really not useful. So again, there is no hope with this approach, because what we ideally want really something like a second order SGD. That's what we want, something like this. We want to have a method which is second order and can work even with just one data point at a time, just like SGD. Mini batching is an extra trick which we might want to throw in if we want that, but it shouldn't be necessary. And this approach doesn't lead there. So there's been a very beautiful line of work by Farber Rusta, Michael Mahoney. So this is one of their main papers on the topic in mathematical programming. And these methods are quite useful in practice. They improve on, let's say, classical Newton's method and so on. But in theory, they don't have the second order properties unless these mini batches are really, really huge. Okay, so these I called attempts which don't quite deliver on what we want. So I would say that there is really no stochastic second order method that I know of which use small mini batch size. So not something like kappa over epsilon squared, but small, O1, let's say, which has a local convergence rate, which I wouldn't even say quadratic, but just independent of the condition numbers. I want to have some property, second order like properties, something which resembles the properties of Newton's method. So this is the goal. Good. So I'll stop here again because I'll be moving to the development of the actual method now.
Yeah, Torben has a question.
Yeah, thanks, Peter, so far for the talk. It's really interesting. I was wondering, with these stochastic second order methods, so how I understand this, that I take this inverse Hessian works kind of as a preconditioner. And then if there's a way that I know that certain FIs are kind of really what drives the condition number up, could I just kind of fix these functions FI and then take them as the kind of fixed preconditioner and then, don't do anything stochastic on the Hessian, but just fix these? Would that work?
But you'll still be computing the true Hessians?
Probably
Or just for fixed set of indices, but you'll still be computing the Hessians.
Yeah.
Well, this could work, but only in the case where the function really is low dimensional intrinsically. So when all the action is in some lower dimensional space and you somehow knew it, then this could work. But this is not the assumption I'm willing to make here. Because once you knew this, in fact, what you're then running is full Newton's method in that subspace.
Yeah.
And without that assumption, this is not going to work. I don't think so.
Yeah, thanks a lot. Thanks.
Any more questions?
I don't think so. Not for now. Thank you.
Okay. So now I'll construct what we call a stochastic Newton method, which will have these properties that we desire to have. And I will give two different constructions. So one construction and second, they're equivalent, but they lead to equivalent algorithm, but they're different constructions. So here is the simple one. So I'll take the Newton's method and I write it in this funny way because I know that my function is average of a bunch of functions. So I know that the Hessian is just the average of these Hessians of these individual functions fi's, and I know that the full gradient is just the average of the individual gradients. So this first line is nothing else than just Newton's method. And now what I'll do, just a very simple reshuffling of what's going on here. I'll just write this vector xk as inverse Hessian times the Hessian times xk. Okay, I didn't do anything else than that, and then I just reshuffle this a little bit. So that's all that's going on here. And now, okay, and now I'm going to do this. I'm going to get rid of xk. Okay, because I'm constructing my method now, and instead of xk, I'm going to say that there be some wik. What have I just done? I have just allowed every single function, fi, to own their own iterate, which I call wik. So in some sense, I have lifted my problem from d dimensions, where xk was d-dimensional, into d times n dimensions, because now I have n vectors of size d. All of them are vectors wik. Okay, and so that's what I'll do. And now I almost have an algorithm. Okay, if you give me wi case, okay, I can just plug them into this formula, into this right-hand side, and I get xk plus 1. But this is just half of an algorithm, because then I need to get the next w's from this xk plus 1. And if I'm able to do that, then I have an actual algorithm. So I'll come up with the rule, and this is the rule. I define the next w as a function of this xk plus 1 and the previous w's. And the function is randomized, and this is where the randomization is hidden. So what I'll do, I select a random set of indices, sk, and in iteration k, and this randomness is IID throughout all the iterations. So in fact, what I do, I choose a random subset of all the functions, which is uniform. So from all the, let's say, subsets of size 10, I choose uniform and random. Or from all the subsets of cardinality 25, I choose one of them uniform and random. So this is what this sk set is. But the cardinality could be anything, could be even 1, could be 2, could be 3, could be anything, could be n, could be the full set. And then notice that I'm updating only those w's for the i's belonging to the set sk. And the rest of the w's I just keep intact. I'm not updating them. And this is a full algorithm. And this is in fact the algorithm which we call stochastic Newton's method. And this is the method which we analyze. So I claim that if you do things this way, then you only need to do, maybe I have a slide on this, let me see. I mean, I don't. Maybe I have it later, I don't know. I wanted to add it at some point. So so the property that you have for this algorithm is that in each iteration, you only need to compute as many stochastic gradients and Hessians as is the cardinality of the set sk. So by the cardinality, you control how much work you do in each iteration. And plus, you have to compute one inverse of one D by D matrix. Okay, I'm not going to be cheating on this through some BFGs updates or anything like this. I'm actually computing an honest inverse, or well, I can just solve this linear system to compute the right-hand side, so I don't actually need the inverse. But I will be either inverting or solving a linear system of that type. Okay, so I'll pause here for a moment because this is really the main algorithm here, and I want to make sure that at some level this is understood. Even though I'll construct a different construction, I'll explain different construction in a few moments, but I want to make sure that this construction is clear.
Oh, yeah, there is a question, possible question from Shaheen. So,
yeah, hi. Quick question.
Hey.
Can you use the same trick for stochastic gradient descent? So you do the sum over all the gradients of Fi's, but you only update a few of them. Because it seems that this trick could be used just.
No, in stochastic gradient descent, you compute few stochastic gradients, but you always have just one vector that you maintain. You only need the X, you don't need any W's in SGD. So SGD really lives in RD, but this doesn't live in RD because I replicate this XK and I create n copies, which I call WIK. So this is different.
Yeah, sure. I understand that, but my question is, if you just take gradient descent and stochastic gradient descent, then you somewhere between the two, you can use this idea where you take the sum of all the gradients, but you only update a bunch of them, right?
Yes.
So
okay. So I see what you're trying to say. Yeah. So you can do a similar thing for a first order method, just like this, but for the first order method. And in fact, you can even keep those WIKs around. And in fact, I'll comment on this in the second construction.
Okay.
I believe that should be clear. So a first order method of similar construction to this already exists, and this is called the MISO method.
Okay.
I'll comment on this.
Thanks.
So I really want to pause here because if this is not clear, then I shouldn't be continuing. So it's much better if we have a discussion on this, and then we're just jumping away to the next slide quickly.
There's another question from Margaret.
Hi, it's maybe not a question, but I'm sort of struggling to get my head around why this is sort of less updates than the sort of full Newton methods. Could you explain that again?
Oh yes, okay. So it's because if you look at what I'm doing here at this step. Yeah. I'm computing this matrix, which is average of n matrices, right?
Yeah.
Then I'm inverting it and I'm applying this to this vector, which is again average of n vectors. Okay.
Yeah.
But imagine that I stored all of these Hessians somewhere.
Yeah.
So there's lots of memory here. Okay. I have them stored. Then I only change some of them, only those that belong to the set. All the others, they don't change because the W is the same. So let's say that set SK has cardinality 5 only, okay?
Yeah.
Then once I computed these n matrices, only 5 of them change.
Okay, yeah.
So I can simply just take the previous matrix that I had computed, subtract from this 5 matrices, and add new 5 matrices, and I have this as at the next iteration.
Yeah.
And the same thing applies here. So at twice the cost of, let's say, 5 or cardinality of the set, I can do this. So it's simply independent of n. It just depends on the cardinality of SK. I mean, the computation of this matrix and the computation of this vector only requires as much work as is the cardinality of the set SK, maybe twice that, but independent of n.
Yeah. Okay, that makes sense. Thank you.
Okay, so I'll move on, but feel free to interrupt me after this at any point. So this is the algorithm written again. I don't think this slide is useful, so I'll just skip through it. And here's some comments on what's going on here. So at the beginning, I need to compute all these n hashes and gradients. Because at the beginning, I just started with some w's. And these w's could really be anything, any estimates. So let's say they're all the same, even the same vector. I have to compute all of these Hessians and all of these gradients. So that's the first step here. So this is the amount of work. And then I also have to store all of these n gradients and n Hessians. So there's lots of memory requirement, O n d squared. But then in each iteration, I only need to compute tau gradients and tau Hessians, where tau is the mini batch size. So this is the size of the set SK. For exactly these i's in SK, okay? And then I have to compute this one inverse matrix or solve in a system. Okay, so I'm assuming D is small. I'm assuming this is not the bottleneck. The bottleneck is n. N is really huge, D is reasonable. So this is really what's going on in this algorithm. Okay, so here's a different construction of the same algorithm. And the construction actually follows this logic. There has been an interesting new method developed about 7 years ago called MISO by Julien Mayral, which is to gradient descent what stochastic Newton method is to Newton's method. So I'll first explain how you get MISO out of gradient descent. And then in a similar way, we actually get stochastic Newton out of Newton. Okay, so that's really the logic here. Okay, so we start with gradient descent and we write it in a funny way. So we write it as xk plus 1 is the argmin of a certain function. And the function is just average of these model functions phi ik, where phi ik just happens to be this. So what is this? This is just a linearization of function fi at the current iterate xk, plus Lipschitz constant of the gradient divided by 2 times this quadratic perturbation. So if you minimize this function, you just get the local gradient descent for a function fi. If you minimize the average, you just get the gradient descent step. Okay, so again, you may think of all of these methods as simply minimizing some model of your function. So the original function is average of functions fi x. And now every fi, I just replace with some model of what I think the function actually is well approximated by. And to the first order, good approximation of fi around xk is this. Okay, this is just Taylor expansion, but in fact, this happens to be upper bound on the function under convexity. Okay, so then gradient descent simply is minimize this, and the way you can see this, just set the gradient to 0, solve for xk plus n1, and you get gradient descent. Okay. Now, how do you get MISO out of this? Well, MISO, which was developed by Julien Mayral in 2013, and in fact, a little bit later on, independently, the same method called Finito, which is the same method by Aaron DeFazio and co-authors, is in fact one of the very first, but not the first, but one of the very first so-called variance-reduced methods, SGD type methods. All of these variance-reduced SGD type methods, they really started in 2013, so you can see it's really in that year when this business started. And well, actually, there was SDCA in 2012 and SACA in 2012. So this is really the first 2 years of the development. And there's been a lot of development in this area. There's SRE, RG, and SAGA. You might have heard of these kinds of methods. And many more. There's actually hundreds of different variants of these methods. And all of them, in fact, have you can think of identical theoretical properties, so that they behave slightly differently. This is not that important. What is important is that we will need a variant of this MISO method, which is a mini batch variant, which in fact, with my postdoc, Shun, Tian, and Ali Beg and Konstantin, my students, we analyze it recently with some different proof techniques, and we got good theoretical rates, something that one would expect rather than the existing rates. And that's the method that I'll describe now. So it has exactly the same form as GD. So I'm minimizing average of these model functions, but these model functions will now be different. And how is this model function different from before? Well, only in that instead of xk here, blue xk for every single point here, I have wik. So I allow all of these vectors to be different. Okay, so if I just go back, you can see that this is really the same model function as this one, except this xk I replace with wik. Okay, and that's it. Then xk plus 1 can be just written in this way. And I need to, of course, then update w's, and I'm updating them exactly the same way as I just described for stochastic Newton method. So this was not in the original MISO algorithm, but in the mini batch MISO algorithm that we studied, this is the update, which I already explained. And then if you actually choose the mini batch size to be everything, then all these w's are forced to be the same, and MISO just happens to be gradient descent. So you can think of MISO as a generalization, stochastic generalization of gradient descent with some nice theoretical properties. And now Newton's method does something very similar. It also minimizes average of some model functions, but these model functions don't use just a linear approximation plus simple quadratic, but a quadratic where the Hessian is actually the local Hessian. Exact local Hessian, not bound on the largest eigenvalue of it, but the actual Hessian. And now that you have that, if you just minimize this average, what you get is Newton's method. And this is very easy to verify. You just sum up all of these model functions, you get this thing. Actually, you should have the constant term there as well. So sorry for that. And then you take the gradient of this, set it to 0, solve for it, then you get Newton's method. And now you can already see what I'm going to do. I'm just going to replace every xk, every blue vector out of these 1, 2, 3, 4, 5 vectors by wik. And that's stochastic Newton method. Okay, it's not exactly how we obtained this, but after we obtained this, we realized this is one potential way of thinking of it, which is maybe good for slides about the work. And I claim this is really the stochastic Newton method. It could be written in this way as well. And the iteration is this, which is equivalent to what I was writing about before. And again, we have the same property. If the mini batch size is everything, so if we make it non-stochastic, then all these w's are forced to be the same because of this update, right? All of the w's have to be xk plus 1. And then stochastic Newton recovers Newton's method. Okay, so here's a summary of all of these. All of these four methods have this form, minimization of the average of these model functions, but these model functions are different. And MISO is to gradient descent to what stochastic Newton is to Newton's method. So again, I stop here, and then I go to theory. And please tell me how much more time I have, if any.
So we have 8 more minutes, or yeah, we have 8
That's
more
perfect.
minutes. This should
That's
also
good.
include questions, but we had questions during the talk, so perhaps we don't need to leave so much time for questions. But yeah, that's it.
Yeah, I'm just happy here to take questions now. And okay. Okay, good. So if this is clear, then I move on to theory, and at least want to make sure I go through this main theorem, which will be easy because this is just really one slide. So this is the main theorem. The theorem says that a certain Lyapunov function goes down at a certain rate, and I'll explain what this means. But let's first think about what actually goes down, what decreases to 0. It's the average square distance of these red vectors wik's from the optimum. And with the assumptions that we make on these functions, that all of them are strongly convex and have Lipschitz Hessians, there's a unique minimum. We call it x star. And if this method is any good, then better all of these w's converge to x star. So we'll simply say that the average of them is the quantity we're interested in, and this is what we want to push to 0. Okay, so that's it. Now, what is tau? Tau is just the cardinality of sk, but sk is a random set, so we can just say this is the expected cardinality of set sk. So this is the mini batch size, and I allow this to be 1 or 2 or 3, whatever we want. We can set this. This is a parameter of the method. H is just the constant, the Lipschitz constant of the Hessian. and mu is just the strong convexity constant. That's it. Okay, so now how should we think of this result? One way to think of this result is to ask question, do we recover the local quadratic rate of Newton's method if we specialize this method to Newton's method? So if we choose tau to be n, then this becomes Newton's method, as I explained. Do we recover the local quadratic rate of Newton's method? And the answer is yes, because if tau is n, then I think I don't have it written there like this. Okay, if tau is n, then tau over n is 1. This cancels out with this 1. Okay, so this is gone. This is gone. So all that you have is just this constant times wk squared. And this is precisely how you get local quadratic rate. So if this wk is small enough, then the next wk is smaller than a constant times the previous wk squared, and this is local quadratic rate. And in fact, it's the same rate and the same neighborhood as that for the classical Newton's method that you'll find in textbooks. So we recover the same rate precisely. So the same method and the same rate. But now we have a more general result. So you can think of this as generalization of Newton's method, which it is. And then the rate is different. And one thing to say is that the method, as soon as you randomize, the rate cannot be, and it's not quadratic. And that's because of this thing here, 1 minus tau over n. Once you have the 1 minus tau over n, this 1 minus tau over n is not multiplied by any wk, unlike this part, which is multiplied by wk. So there's always at least 1 minus tau over n times this wk, which is slowing us down. So the rate can only be linear, but it will be independent of any condition number. And this is what I'm going to mention in the next corollary. So as soon as I'm close enough to the solution with every wi, then what happens is that the expected Lyapunov function is going to decrease at the rate 1 minus 3/4 of the mini batch size divided by data set size. So this is a linear rate, obviously, but you can see there's no conditioning anywhere. It's independent of condition number. And this is precisely what we wanted. We wanted to have a rate which is independent of condition number. So this is not achievable by any of these first order methods, whether they use mini batchic, momentum, per coordinate step sizes, whether they're Adam or whatever they are. If they are first order methods, they cannot possibly have a rate independent of the condition number. But this randomized method does have such a rate, and it's thanks to its second order nature. Okay, so I'll stop here for any questions, and I understand I have 3 more minutes.
Can I ask so do these results suggest how you should set tau in practice, and does it actually work to set them according to this?
No, these results don't suggest that. This really depends on how much does the rate improve compared to how much more work you need to do to compute these extra Hessians and extra gradients.
Mm-hmm.
And this varies from application to application. If you have a very, very generic result, generic problem, where, for instance, you actually are forced to store all of these Hessians and store all of these gradients, then the method as described here might not be as practical as it would be if, in fact, you can apply some shortcuts. So, for instance, if you have linear models and you can, instead of remembering the gradients, you just remember some scalars and these kinds of things. If you can apply these kinds of tricks, then things will tilt in your favor.
Okay.
So at the moment, I think of this as really just a starting point for the development of practical variants of this. Now, we did some experiments, and I have some slides on this, and some of them are encouraging. Some of them are a little bit discouraging because we really run the method as analyzed, but at least the theory is the theory that we wanted. We get this independence of the condition number, and the other question is how can we really make this more practical using maybe quasi-Newton type approaches, globalization approaches, how to solve this issue with memory and these kinds of things. So one has to ask these very practical questions, and answers have been provided for first order methods for all of these questions. And now we will need to provide these answers for extensions of the second order method.
Okay. Thank you.
You're welcome. So I don't have much more time. I have 1 more minute. So maybe I'll just stop here, in fact. So I can show you maybe 1 slide with experiments if you want, or I can just give extra space for 1 or 2 more questions.
Yeah, if you please could show a slide with experiments.
Okay, so I'll skip through this part, which I knew I wouldn't have time for. So we have a cubic version of this, cubically regularized. I just go through, I just skip through it. Okay, so there's some rates for this, and maybe I'll just describe this 1 experiment here. And this is for the cubically regularized variant of this method. So what we'll be comparing is we're comparing the full cubic method, the deterministic method, and the stochastic method. And on this particular experiment, we can see, first of all, that the stochastic one is better than the deterministic. And we can also see that the number of iterations, in fact, is not affected by the conditioning, because once we set the lambda, the L2 regularization, to something really tiny, then the condition number really just blows up to something really to infinity. Okay, it's absolutely huge, and still this thing behaves very nicely. So it does have this property of independence of the condition number. So first order method could not possibly have this type of behavior, and stochasticity can lead to a method which is faster than the deterministic method. But again, this is preliminary. We didn't exactly observe always better behavior for the non-cubically regularized version. Sometimes yes, sometimes no. So effort is needed in making this more practical. And there's lots of tools that have been already published in the first order world, and we should be trying to do that in the second order or the world now. My time is up. Thank you very much.
Thank you very much for your talk. Yeah, I would like to give the last opportunity to ask any questions if someone might have a quick question or 2. If I may have just very quick question on your previous slide, you mentioned that
Sure.
like one of the assumptions is that you initialize close enough to the
Right.
The solution, and that seems to depend. Is mu the condition number?
That's the strong convexity constant, and H is the Lipschitz constant of the hashing.
Okay. Thank you.
Yes, so this is the nature of the local quadratic convergence, even of the classical Newton's method. So Newton's method, as designed without any changes, is actually not globally convergent. There are counterexamples, it can diverge. So it has to be globalized using maybe some damping or using cubic regularization or something of this type in order to obtain global convergence. But here I focus on the non-globalized, non-cubically regularized method. So I wouldn't expect behavior which is different from classical Newton's method. After all, we recover Newton's method in the extreme case of full mini-batch size. So we were aiming at local convergence result, and we do get local convergence result. And the local, the size of the local neighborhood is the same as you would have for Newton's method. So this is the best thing that we could hope for, but it is a limitation.
Thank you very much for your talk again, and thank you for finding time to speak at Mathematics of Data Science conference.
It's my pleasure. Thank you very much.
Thank you very much. So yeah, with this we finish the optimization section, and we will move to the next session on Bayesian methods.